Hi everyone. I wanted to create a video to show you how to fit a regression model. And when I say fit a model, I'm talking about finding the best model. And the principle here is something called parsimony. Parsimony means that we make the model complex enough to be useful and accurate, but not any more complex than that. And so we want to get rid of any extra baggage, if you will, and keep our model simple while effective. And here we have a data set that came with the textbook. It's a data set of 67 cereals, and they give us the calories and other nutritional information in the cereal. And the goal here is to figure out which of these nutritional factors contribute most to the calories in the cereal. And so when we set out to fit a regression model, one of the first things we have to decide, just like any regression model, is which of these variables is our dependent variable, our y variable. And in this case, that's going to be our calories, because we're interested in what contributes to the calories. So we're just going to go ahead and highlight that a different color to keep it straight. But then the next step is we want to understand how all our variables correlate, because there's this problem called multicollinearity, and that's a problem when among the x variables, the independent variables, there's high correlation. It can cause a lot of problems in our regression model. It can cause the numbers to go ski-wompy and uninterpretable. So if you ever see a model that just doesn't make sense, you're probably suffering from multicollinearity. So to avoid that, we're going to look at how our variables correlate amongst each other. So we're just going to create a correlation table using the data analysis toolkit. So we'll include our y variable. Make sure we click labels, and we're just going to output it to a new worksheet called Coral. So if we take a look here, we'll pretty this up so it's a little more readable. Based on the book's criteria, we're interested in finding correlations above or more extreme than 0.7, and that would also include more extreme than negative 0.7. And keep in mind that multicollinearity only concerns itself with the x variables. So as you can see here, we don't really have any of these variables that correlate highly with each other, so we're okay. And what that means is we can start our initial model with all 4 of those x variables in our regression model. Now, keep in mind that when it comes to our y variable, our dependent variable, correlations with the x variables is actually a desirable thing. So we don't worry about high correlations with our y variable and x variables. So like I said, that tells us that we can actually start our initial regression model using all our independent variables, our x variables. So let's go ahead and fit that. So our y range is going to be calories. Our x range is going to be the 4 other nutritional factors. Make sure we do labels, and I'm going to stick this out, and I'm going to call this all, because we're including all the variables. So now let's take a quick look at this output of the regression model. When we are fitting models, we don't worry about looking at all the normal statistics like the significant F, the p-values, the r-squared. We are just concerned at looking at the adjusted r-squared. So the process we're going to go through is we're going to take hints from the p-values, and really just the 4 nutritional factors here, not the intercept. And we're going to look for p-values that are above 0.05, and in this case those two are above 0.05, so we're going to highlight them and we're going to remove one variable at a time. And what we're interested in watching is whether our adjusted r-squared goes up or down. If it goes up, we keep the variable out. If it goes down, we need to put the variable back in. The goal here is to maximize our adjusted r-squared. So again, when we're fitting models, all we're concerned about really comparing is the adjusted r-squared between models. So let's go ahead and go back to our data, and we're going to start by taking sodium out of the model first. We can do that. We'll go revisit our regression, and notice I'm just going to highlight the last three columns for our X range, and that takes sodium out of the model. And then I'm just going to keep track of these. I'll call this minus sodium. Now take a look at our adjusted r-squared. If you remember, when we had our full model with all of the variables, our adjusted r-squared was 0.275, and when we took sodium out, it dropped to 0.720. I said 0.275. It was 0.725, and it dropped to 0.720. So our adjusted r-squared went down when we took it out. So that means even though the p-value back here for sodium was above 0.05, we're going to keep sodium in our model. And so then the next one we're going to try to take out is fiber. And since fiber is kind of in the middle here, we're just going to cut it and paste it off to the side here. And then we'll get rid of that column. Now let's fit our model without fiber. We'll call this minus fiber. Now again, look at our adjusted r-squared, and it went down to 0.724. So we have to compare this with our full model, 0.725, because this adjusted r-squared only makes sense when we compare it among nested models. So the variables in this minus fiber model are a subset, those three, of all the variables in our original model with all of them. And so we have to have a subset of the original model to compare it to, and that's what this minus fiber is. So since it went down to 0.724 from 0.725, we're going to interpret that to mean that we need to keep fiber in the model. And we'll talk more about it not being a hard, fast rule in a little bit. But then we can go on, and just because these p-values are significant doesn't mean that they should be in the model all the time. Usually the p-value is a pretty good hint. But let's just go ahead and take carbs out of the model. I'm going to put carbs off to the side. Bring fiber back in. Fit the model again, and I think it's already set up, but just in case, we're going to choose those last three columns, and we're going to call this minus carb. And now, as we expected, because the p-value was so low, look at what happened to our adjusted r-squared. It actually went down quite a bit from 0.725 to less than 50%. So one thing you should pay attention to is notice our r-squared, it's 51% here. Compare it to our r-squared of our full model, 74%. If we go look at fiber, it was 73%. 73%. But yet our adjusted r-squared went down when it actually went back up. What's important to understand is that your adjusted r-squared penalizes more variables in the model. So if I stuck some random unrelated variable in this serial data, like the position of the moon, my r-squared would go up, but my adjusted r-squared would go down. That's why it's important that we use the adjusted r-squared to compare our models. So the key takeaway here is, as we create different models, we look at the adjusted r-squared, and if it goes up, we keep the variable out. If it goes down, we put the variable back in. Now, just a side note, let's say we decided that 0.720 isn't that really big of a difference from 0.725. Same with fiber, it went down to 0.724. So let's actually say that we decided that wasn't a big enough difference in the adjusted r-squared to merit keeping it, because after all, is it really practically significant if adding fiber in there only helps us explain? See, there we got 73.7. With it in there, we have 74.2. We're even, it's less than 1% more explanation of the variance in calories. So in the spirit of parsimony, we might argue we've got enough evidence here. If you look back here at the fiber p-value, is well above 0.05. When we took it out, our adjusted r-squared only went down to 0.724. And so maybe it's not adding that much to the model. See, just like our significance level, it's a rule of thumb. So let's go ahead and say, alright, fiber's not really adding things to any useful information to the model. So we're going to take fiber and we're going to take it back out. So let's take fiber out. Away with you, fiber. Let's put carbs back in. But this time, we're going to take sodium out. And since carbs and sugars are right next to each other, I don't need to move sodium. We're going to go ahead and take sodium out. And you'll see that we have to compare the adjusted r-squared with its closest nested model. So let's go ahead and do that. I'm going to change our x variables to just be carbs and sugars. And then I'm going to say minus carb, actually minus fiber and sodium. So now the model that includes just one more variable than this is our minus fiber model. So we're going to compare the adjusted r-squared between those two. Let's pretty it up so we can read it. And take a look at our adjusted r-squared. It's 0.717 compared to our fiber, which was 0.724. And if we even go up one more outer nesting, 0.725. So 0.725 compared to 0.717. It didn't really go down that much, given taking those out. It's not adding that much more explanation having them in. We're still explaining 72.5% of the variance in calories. So we could in this case, we could make two fairly good arguments. One in favor of this model right here, because why worry about calculating fiber and sodium when we can just plug in carbs and sugars to estimate our calories, or to figure out what the calories are attributed to. We could also make the case that since this had the highest adjusted R squared, we could keep them all in there. And it's really a business decision. So in this class, a lot of times I'll just have you maximize the adjusted R squared. So the full model with all of them would be acceptable, and the fiber and the sodium would be acceptable. But let's go ahead and say we took the fiber and sodium out and we accepted this model. Let's go ahead and answer the question, what would our final equation look like? I'm going to copy these over to our data. I'm just going to paste them over here to the right so we can, or down here below so we can see them. Our regression equation would then be calories equals 3.35, some little round, times carbs plus 3.91 times sugars plus our intercept 28.76. And that would be the equation that we would then use out in practice in our business to actually calculate or estimate the calories in the cereal, or to explain what the calories are attributed to. So that's model fitting. And the idea again is parsimony. Only stick stuff in that really makes an impact. So that's one of the reasons we ended up with just 2 variables in there instead of 4. Hopefully that's helpful.